Okay, I'm all set. Hi. All right, how is everybody? Yeah? Well, I was gone to the NLP conference where our group has presented 3 papers. Some of the material was covered in class already. And did you enjoy the 2 lectures last week? We have Harsha talking about yeah? Good, I'm happy to hear that. Harsha was talking about the Genie framework. And of course, you've done the homework and you got a chance to look at what goes inside and how we created that. And then on Wednesday, we have Jackie. That's very different, isn't it? And the point really is that voice or text interface is just not enough. I mean, you really have to combine that with GUI as well. That combination is non-trivial. And what Jackie did was to show how you integrate the two in a fundamental way so that it can actually be used in complex situations, such as situations where you can even talk about using voice for working with, say, PowerPoint, okay, where you actually take it to the level where you're dealing with real complicated hardware. So anyway, I thought it would be great for them to talk about the work since they have been working on this for a while and have very good insights on this topic. So for this week, we're going to do something a little bit different, and that is that we're going to go under the hood. We talk about some of the tools that we have been using, we just assume, and let's get into the details of that. So there are 2 topics that we have alluded to. One is information retrieval. We have this black box. We say, here is a text. Go find me the 1 paragraph in the billions and billions of text, paragraphs of text, and find me the right one. And if this does not do well, it doesn't return the right paragraph, there is nothing you can do. Game's over. So it is very important to find the right text. But of course, that's a very hard problem because there's a lot of text on the internet or even in the WikiChat project we did. Wikipedia is very large. So how do you do that? So that's problem number 1. The second one is entity disambiguation. If I have to understand you, I have to know what you are saying. Suppose I take something like Lincoln. If I say, how tall is Lincoln, what am I referring to? Obviously, it's a person, and that is Abraham Lincoln. But if I say, where's Lincoln, Nebraska? The city is named after Lincoln, but now that's a city. So that's a totally different meaning. We're not asking where, so you have to know which Lincoln it is that I'm referring to. And that is somebody who's really famous, but even that is ambiguous in terms of what it could refer to. So if you don't understand what we are referring to, you won't be able to answer the question. So those are 2 very important questions, and it requires a lot of work to solve this problem. So we're going to have 2 goals. We're going to talk about information retrieval. We're going to talk about this idea called late interaction model. And it is all about scale. Billions and billions of paragraphs, find the right one, or find the top 10. Okay? How do you handle scale? It's all about making it accurate enough, but at the same time fast enough. Nobody wants to wait forever. Right? So there is a question of time optimization and space optimization, and that's what we're going to talk about. With respect to named entity disambiguation, we're going to talk about how we figure out what it is. There are 2 pieces of information that are useful, which is entity description and type information. So those are the topics we're going to go over, and that basically is the outline for this course, for this class. So for information retrieval, we're going to talk about 2 very, I would say, seminal papers. That is in 2020, and this is actually developed at Stanford with Professor Zaharia Matei and his student Omar, who did this work. And the project is called Colbert. Well, BERT, right? Everybody knows BERT. That's a language model. But who is Colbert? It's the comedian. It's very clever. It is contextualized late interaction, so that's how you get the COL. But there is a wonderful question whether we should call it Colbert or Colbert. Are you talking about the science or talking about the person this seems to be named after? Okay, anyways, so that's Colbert. That was 2020. And it has over 1,200 citations. Because when you solve the text retrieval problem, tons of people are using it. And it is really one of the well-cited papers in this space. And 2 years later, in NACL, they presented Colbert V2. And that's when they improve it one more round using space compression. So what is it? So here is the basic idea of information retrieval. You have tons and tons of data out there, and you need to find it. So you start with something like a question. What compounds protect the digestive system against infection? Do you know? It's a good question. Somewhere in this text is the data, is the answer that you want. So the question is, how do we find it? So you have to find these paragraphs that refer to them, but they don't just answer that question. It is kind of embedded in whatever text, whatever information that they want to write about. And in this case, it just talked about in the stomach, gastric acid and proteases serve as powerful chemical defenses against ingested pathogens. So they don't use the exact word, but you have to understand the meaning, and then you have to be able to pull it out of all these different paragraphs. So, for example, if obviously, this is a good old problem. In the good old days, even at the beginning of near the beginning of the internet. Excuse me. Even if we talk about Google search, you get some keywords, you could go find it. So at the beginning, it was using very basic keyword search. And of course, we really want to do it at the semantic level with my voice is going away, with NLP. So this is a very important concept and can be used in many places, from product search, question answering, fact checking, informative dialogue, and so forth. So it is really fundamental and very basic. So how do you do that? It is really all about scale. So there's quality and efficiency. It's interesting to look at what we have done in all these various different years. In the history. So MRR, I'm going to talk about that. It is a data set, and MRR top 10 at 10 is whether you can find the right paragraph within the top, the 10 paragraphs that you retrieve. And, it is, we keep creeping along at this 20-ish percentage, and the latency is of the order of 100 milliseconds. And what we want is, of course, higher quality, and of course, we want lower latency. So we want to be at that corner. So when BERT first came out, now we can use the deep language model, and you get a jump in the quality, but at the same time, the latency went all the way up. This is a log scale. So now you're talking about 1,000 level of milliseconds. And so what Colbert did is that it brings it down. It brings it down to, roughly the same amount of time, but now we are at the 35% accuracy, and that's Colbert. And then the other one is that with Colbert V2, it takes it to a better performance and also at a lower latency. So this is, so it makes a huge difference. And so, as you can imagine, Colbert is built on top of BERT. So the question is, how do you do this? Something on my throat. All right. So the basic idea is that you have a question, and now you have to figure out for each document out of the gazillion documents you have, what is the match? Okay, you want to give it a number, the match between the query and the document. And unfortunately, if you give me a query, I have to check against all the documents that we have. That's a lot of document. So for each one, we're computing a value. And then, of course, we want to pick the 1.93 over 0.01 and so forth. So in a dumb method would be that you just go through, pick a pair of a query and a document, compute the score. Hundreds of millions or billion paragraphs later, you have that many scores, and you sort them and you find the best one. So how do you even design or compute the score? How do you build the retriever? So obviously, we're going to do training, and this is a very important data set. This is an IR data set. It's called MS Marco. It's produced by Microsoft. And it is a human-generated machine reading comprehension data set to start in 2016. And in 2018, it just turned into an IR data set. So the important thing is that we are really working with real user queries. I emphasized many times. You give me fake queries, it's a totally different thing. You don't say, here's a paragraph, what is the query for it? This is actually 1 million real-world queries from Bing. And in order to answer these questions, it came from 8.8 million passages from the web pages. And the metric, there are many metrics, and one of them is MRR 10, which is to find the right answer within the top 10 documents. So this is the starting point where you have question and paragraphs, okay? Because we're not trying to figure out what is the sentence that is closest to a paragraph, because a question is not the same content. You're asking about what and when and so forth. It doesn't match the content exactly. So what you are trying to say is, given a question like this, what is the right paragraph? So this requires a data set, and this is a hand-annotated data set. So how do we go from there? You now have a data set. So I'm going to talk about 2 extreme matching paradigms. The first one is a good old, a classic cross encoder. Okay, you have a query. It's broken down to tokens, documents the same way. And you have a network that you train, knowing that in the end, you want to compute a score. The ones that match have a high score. The ones that don't match, low score. So that's the encoder. And it is, this is the best you can do in a sense, given the data set. Okay? So this is, you get fine-grained interactions between the queries and the documents, and they match all the way up. But on the other hand, that's very expensive. Okay? You have the hundreds of millions or billions, let's say billions documents to begin with, billion paragraphs to begin with. Every single question, and you're going to compute against all these documents. Okay? It's a very expensive neural network to train, and it's also a very expensive neural network to use by the time you actually, you want to find for each query what the answer is. So there's training time and there's inference time. And this is just not doable. It is too expensive. And so if you suppose you finish training, if scoring each document takes only 10 milliseconds, that will consume 11 days with 100 million documents. Okay, so this is seriously undoable. So what do we do? What do you think we should do? What is interesting to note is that queries and documents are two totally different things, okay? The documents are fixed. You have a set of documents that are fixed from, whenever you want to do this lookup. But the questions come in, and every one of them is different, okay? And so what you really want to do is to do something separately. So given the documents, you should do whatever you need to handle the documents ahead of time, and then you can quickly take care of the new query that comes in. So that's very important that you separate the inference from the, having to go through all the document one at a time. So the idea here is to have a bycoder. The bycoder is to separately find the embedding for the query, for the document, and then you take the, you take that and you do a similarity comparison, right? You find a similarity score for the queries in the documents. And what that means here is that the documents can be pre-computed once and for all. I mean, you still have to go check against the document, but you don't have, you just take the final embedding that you can compute for that document and compare it with the query that comes in. So that solves a performance problem in a significant way. And so we now have this independent dense encoding, but it is pretty coarse. Okay, so yeah, I'm training this whole model using the question and query data set, but you're now just talking about, in the end, a summary of a document. But if I give you one document, or if I give you one document, there are many, many questions that you can ask about that document, right? And if I just summarize it in one way, how is it going to match that particular query? So you cut the connection, but at the same time, it is a lot coarser. So that that hasn't worked too well at that time. So what Colbert suggested is that we're going to do late interactions. That means that we separately, when we calculate the embedding, they are separated. But at the same time, we then add a late interaction connection above that. This late interaction allows you to take each vector from the query and compare it. You see, you're doing a max sim, which is like a maximum, is some kind of maximum similarity, such as cosine similarity. Okay, and for each vector here, for each element here, you can now do a maxim against all the entire vector, all the vectors from the document, and one at a time, you're accumulating each of these elements together, and then you can find the max sim. Okay, so this has got a lot more interactions between the queries and the documents, and it's not just one value for the query and one value for the document. So you get the choice that you get some advantage, because if you look at the embedding for the document, it is an offline encoding, but it is not turned into one aggregate value that you do cosine similarity. You leave them as n-dimensional vectors, but you can pre-compute them. And then at that point, after the query has been encoded, you can now do this more complicated, more sophisticated interaction. And this is why it is called late interaction. So the important part is that the blues, all this work on the embedding of the document can be done offline once and for all. Okay? And it's not once every time you do the query. And then with the cosine similarity, you are finding the nearest neighbor search. You are finding the query that matches closest. You're finding the document that matches closest to the query. Using this maxim calculations, we sum it up, and then after we get all the numbers, you sort them and you find the top n values that have the highest similarity between the vectors and the documents. So that's the basic idea. So using this method, it was shown that with if you take like 21 million passages from Wikipedia, it takes 70 milliseconds. Okay, significant saving in time compared to the cross-encoder, and much better than the bicoder. So let us take a look at what it means. Here's a real example of the matching. Suppose I have a question like, when did the Transformers cartoon series come out? Have you guys seen them? The Transformer paper, I must say, is one of the hardest papers to read. I don't know if you have that same experience, and people have to explain it using cartoons. So suppose you ask this question. There are many parts to this question, and suppose you have a document that actually said the animated, video or whatever mentions a transformer. It was released on some date. Suppose this is a document with all these different parts. What happened now is that because we don't combine them into a single score for each document, we leave them as a multidimensional vector. So if you look at the query has various parts. For example, for the when part, it is going to match with the on part of that document. And then when you get to the transformers, it is matching the transformers. And when you talk about the cartoon series, it matches the part that has the animated, the word animated. And when it's come out, it is released. So in other words, we don't have a single value for the document, but for each vector each of the dimension of vectors in the query, it matches to the different vectors in the embedding for the document. And this is how you can get this fine-grained interaction, pulling out the right sentence. Any questions about that? So that's the basic idea. So you delay the interaction, and you pay for it only at the last point. So the point now here is that, yeah, that seems to be faster, but we are still talking about 100 million documents. So we have skipped the bottom part, but I still have to do the rest. Obviously, I have to encode the query, and that is not a problem. But I have to now go and compare that. So this is what we do with one document. And now we have to do this for 100 million documents. It is still very, very expensive. So how do we solve this problem? So the paper describes, the first paper describes the first optimization. The second describes the second one. And that is that if you give me a query, I have to find the top K matching documents from, say, 100 million documents. Ranking every document is too costly, so we want to narrow down the candidates. In this process, when we do the narrowing down of the candidates, we're doing it in a coarse way. Okay, we don't have to find the perfect answer. I just have to make sure that the answer that I'm looking for, maybe the top 10, is within the top 10,000. Okay, so I can afford to be not so good. Okay, because I'm going to use a cheaper method to narrow down the candidates. And we're not going to use the late interactions. I'm just going to look at the query and the documents without the fancy late interactions, come up with the match, the closest match for the top 10,000. So we reduce the 100 million to 10,000. That's a savings of like it is like 1,000 right there. After I reduce it down to the 10,000, then you can afford to actually run it through the real pipeline that you have there. So that's the first optimization. The second optimization is on space, and that is that it is, this is a lot of space for the embedding. And when your space goes up, your time goes up. Okay, so the question is, how do we save the time can we compress the space? And that's the second optimization. So for the first one, instead of using this whole pipeline, I want to introduce this concept of FACE, which is the Facebook AI Similarity Search. And this is it's a very, very useful tool, because what it does is that you give me high dimensional vectors, I can give you the k nearest neighbors. Okay, so the math definition is written down here, which is that suppose I have your billions vector x sub I and some dimension d. FACE actually built a data structure in the RAM for it. Okay, so the whole thing does not fit in memory. But FACE is actually optimizing it by building a structure in RAM, and then if you give me a new vector, it will find you the closest k vectors. And what do you mean by closest? Is the one with the minimum Euclidean distance between the x and each of the x sub I, because it's a multidimensional vector, and it will return you the top k, whatever it is that you want. So this is a very well optimized package that is available from Facebook. And so this is one of the basic subroutine, in a sense, that is in CodeBear. So let's see how it works. So we say that there are two stages. The first one is that we're just going to use no late interaction. So I'm just going to look at the embeddings of the queries and the document and find the closest thing. So for example, here we show that for each document we have, it's a n-dimensional vector, so it's an embeddings. And we are using the fast vector similarity search. So when you have a query, you have to go through the embedding. This is all pre-computed. The embeddings for the documents are all pre-computed once and for all offline. And then the query comes in, it goes through the embedding, it finds it calculates the embedding for that particular query. Then it's at that point, we actually look at each element in this embedding. And for each one, we find the closest similarity match with the documents. Okay, each document is an embedding with n elements here, and for each one, we are finding the closest one. And so now we are kind of looking at each part of the query and finding the documents that match each part. Because we noticed that, for the question you really want to assemble it from different parts. So this is what you can do for each of these vectors. And then you figure out what are the documents, given the embeddings that match, you figure out which are the documents that those embeddings, the closest match belong to, and those will be your candidates. That's the result of step one. So we are still talking about finding the top 10,000. Okay, this is not a small result at the end, but you now have the 10,000, and the second stage is to run through the true pipeline, which is the late interaction pipeline. So the concept here is that for each of the document, we go through this pipeline and we get the score. And so forth. And we have 10,000 of them. And then you do a sort and you figure out what are the top 10. So this is how we can find the top 10 closest paragraphs that should answer the question. Okay. So this late interaction makes a huge difference. In the experiment that was run, there were all the various different techniques, and it brings it up from, if you look at MS Marco, it brings it up to the 37.5%, and then for the other, and it is applied to other domains, And for every one of them, it just does a better job using this late interaction. So you are kind of getting some optimization, some advantage of cross encoder and paying the cost closer to the bi encoder. And so this is the result from the paper. But a lot of people, many projects require information retrieval. So they take this module and they apply it to the many different downstream tasks. And it actually does better with a lot of these challenging downstream tasks. And here are just some of the papers that have been using this method. And that was a huge success. I mean, it just, it's like what we just did in the class. I said, look, we're going to call the information retriever, okay? You don't have to deal with it, and it is all done. And this is an amazing module, and it is just very, very much used everywhere. But this is costly. If you look at the Colbert's index, it's an order of magnitude larger than the baseline, 650 gigabytes for Wikipedia. Okay, that's non-trivial. And what it means is that when you look at the size of if you look at the size, it translates directly into cost. So the question now is, can we actually advance the quality advantage and reduce its footprint by an order of magnitude? So that's the question that was addressed by Colbert V2, okay? So if you look at the document encoding, the document for each document, what does the embeddings look like, okay? So, you've got a whole bunch of numbers, and as a matter of fact, there are 128 of them, okay? So it is, is 128 dimensions, and they're these floating point numbers, 4 bytes each. So each vector needs 512 bytes. And what we really want to do is bring it down. How far can we go? How about 20 bytes? That sounds like magic. Okay, so how do we do this? How do they do this? So the concept is to do residual compression. So first of all, you find a set of centroids. Okay, you've got embedding, and they distribute them. You've got all these centroids. So if I have a particular vector that I want to represent, I figure out what is its closest centroid, and I represent the vector by saying this centroid plus a delta, okay? And now I don't have to represent the full numbers because I start with the base of the values of the centroid, okay? So you choose the closest centroid C sub t for that particular vector, and then we can represent this vector knowing the C sub t, the centroid, and then you subtract it and get the residual R. And we do a quantized version because we actually don't need the full granularity of the full 4 bytes for the floating point number, because you have already got the centroid. It takes you to this particular spot, and then you're just trying to quantize to describe the displacement, the residual or the difference, and you don't really need the full resolution. So this is just all a matter of storage. Once you store the data, when you use the information at search time, the information is actually expanded back to whatever it needs to be. So you just have to say, here is my centroid. I give you the index, I pick up the centroid value, you take the residual, you add them back together, and you basically get the approximate version of the original vector. And with this technique, it changes the representation significantly. So we went from 512 bytes, and we just go down to 20 bytes because Whoops, I went backwards. Because we, first of all, encodes the cluster ID, the centroid, which is 4 bytes. And then, because there are 128 dimensions for each one, we actually just use 1 bit. And that gets us to 16 bytes, and altogether, it's just 20 bytes. So this is a huge compression from 512 bytes to 20 bytes. And once you represent this information this way, the question, of course, is, do we lose anything? Do we lose in quality? I mean, obviously, the smaller is going to make the whole thing run a lot faster. And so can we do that? So in summary here is that we represent each vector as a cluster ID and a 1-bit delta per dimension, 20 bytes per vector, and here is the result. Taking the result from V1 we showed earlier, and which takes 154 gigabytes of storage, getting a performance of 36.2. And if you have 2-bit, if you just use 2-bit for the residual compression, which gives you a 6 times compression from 154 gigabytes to 25 gigabytes, the performance didn't change. And if you take it down to 1-bit, which now gives you a 10 times improvement, it just drops a little bit to 35.5. So it was a really amazing engineering solution here to basically just reduce the cost, reduce the time by a significant amount without much of a degradation in performance. So this paper has been cited by over 1,000 other papers, and it's kind of interesting to see what are all the different applications that have been built with it. There are a lot of Best Paper awards that is building on top of Colbert itself, like a white box analysis of Colbert, sparse embed, and it's so forth, how you improve Colbert extensions, and then at the bottom are all the different applications. So this really has a significant impact on the development of information retrieval. So this is work done by Matej and the student Omar, and Omar is now a professor at MIT, and so it's all good. So this is a very, very important building block. So that's the IR part. So what I want to talk about next is that doesn't work. Just give me a second. I'm a little under the weather, if you don't haven't figured it out yet. I went on this trip and I came back. I'm okay. I don't have COVID. I checked, but I'm just a little bit under the weather. All right. So any questions about information retrieval? All right. So let's talk about the second topic, which is named entity disambiguation. And as you see here, we have this optimization where we optimize time by separating the calculation into 2 parts, which is that you select the K candidates, and then you do a more full-blown re-ranking, figuring out what the right rank is among the 10,000 candidates. We actually see the same technique again in named entity disambiguation. So this is something that is useful for you as you think about your problems, whatever they happen to be, that this concept of a coarse grain, filter, selection, and then followed with a more expensive re-ranker. And so let's take a look at the named entity disambiguation problem. So here is the idea. Suppose I give you something like Barack Obama, born in Hawaii, served as the 44th president of the United States. He graduated from Harvard Law School and won the Nobel Prize Nobel Peace Prize in 2009. So there are a lot of terms in a single sentence, and you want to know exactly who are we referring to, which Obama, and so forth. I think that we talked about this entity disambiguation problem last time when we were talking about multilingual. Do you remember? You say that my advisor, he has an English entry and a Chinese entry, but they are the same person. And you have to identify it to be the same person. But the good news is that with Wikidata, every person has a unique ID, regardless of how they are referred to in different countries, and they bring it down to the same ID. So we want to do the same thing here, is that we take all these entities and we bring it down to a unique identifier. So this is Barack Obama, this is Hawaii, and these are all QIDs, these are all the entities in Wikidata. So the question is, how do you do that? So the basic problem of named entity disambiguation can be separated into two parts, which is that the first, I give you the sentence, and you have to figure out when I am referring to an entity. You have to figure out the mention, which is a span that refers to the entity. So in this case, England is an entity, and then the FIFA World Cup, that's the three words together refers to one entity. So the problem now is that you first of all have to pull the mentions out, pull the entities out, and then you have to figure out which entity it is. And so you may be given a knowledge base and an entity list. We've seen this problem before. Do you remember when we were doing the ACLED data? The ACLED data, we're doing the event qualitative coding. It's like I give you a paragraph and I talk about, the military group in India or a region, but you really want to figure out what is the name of the military group. You want to map it to one of these standard IDs, because you can have different newspapers referring to this group in the same way, and you really want to say that this is the activities of the same group. So everything is about tying it to a common global identity. Okay, so we've seen this problem before, and now we're talking about how we're going to be able to do this disambiguation problem. So you have to find out mention, and you have to find the entity. So there are many things that you can use for it. For example, question answering, relation extraction, which is the work that we just talked about. The ACLED work is about extracting in relation, how are things related in an event and given different documents, and they are all related to the same entity and so forth. Automated construction of knowledge base. So in ACLED, we actually put everything together in a knowledge base. So so one of the stronger works in this area is a paper by the group in Facebook Fair, and also University College London and Ecole Polytechnique. And what they wanted to do is to do scalable zero-shot entity linking. Zero-shot means that I want to link something, I want to find the entities, and I have not seen the entity before. Okay, I'm going to train a network on what I have, but then I have to be able to handle new entities that I do not train with, because there are so many entities in this world. And so their key concept here is that we just add descriptions to the entities as input. You don't just give me a bunch of entities and a bunch of documents and say, this one is this one is that. What we're going to do is to add in the descriptions. And once you add in the descriptions, excuse me. And once you add in the descriptions, then you can have a fixed named entity disambiguator that takes this and be expanded to entities that has never seen before. So this is very, very easily understandable because that's, you can do that, and so can a neural network. So, for example, it is a simple sentence like, my kids really enjoyed a ride in the Jaguar. So Jaguar could be a junior roller coaster, and Jaguar can refer to the car. And because we're talking about kids, then the likelihood is that you're talking about the roller coaster. So in other words, this description is entered as input into the system. And now you don't have to kind of memorize by just input-output of sentences and the entities, but you can now take into account the description to find the real, the entity that is most likely related to the sentence that you put in. You see the similarity between this and the query question, the information retrieval? You see the similarity between that? How do I map that to that problem, in a sense? So now this is given. There's a huge difference is that the related elements that you're going to pull out is a lot smaller. Okay? But you don't know which one it is. But now, this entity, how do you compare this with the problem that we just described? Yeah.
The part of my kids really enjoy the riding Jaguar becomes your query, and the set of all possible occurrences of Jaguar within Wikipedia becomes your document set.
Those are your documents.
And it's likely that my kids enjoy a ride at Jaguar would be semantically closer to Jaguar is a junior roller coaster than to a luxury vehicle.
Precisely. So it is, again, a similarity search, a semantic similarity search. But it is applied now to the problem of entity disambiguation. Okay? So all the stuff that we were talking about are relevant here. And so, in fact, they also take a two-step approach. Okay? And the two-step, they could have done this all in one step again if you use a cross-coder. Okay, the fine-grained interactions between query and retrieval. In this case, is the sentence and the possible entities. But that is very costly. So again, we're seeing the same architecture, which is that it has the two-step approach. The first one is a byte encoder, which is that you take the sentences, you find the semantic. You map it into some dense space, the same dense space, and then you can find the closest K entities in this space, the closest neighbors. And what method should we use to make this happen? How do we do this calculation? It's expensive. How do we do this calculation? Huh? What?
Use the centroid, I guess?
Use what?
The centroid we were describing.
The centroid?
Yeah.
The centroid is a representation optimization. Okay? It is try to store the embeddings with smaller number of bits. That's the second optimization. What's the first optimization? Yes. Okay? So you are doing a vector search. You're finding the closest vectors. And again, you can be using the face module. Okay, so keep that in mind because you may find the need for finding similar vectors in your work. So after that, then you do a cross encoder. The cross encoder is the same thing because it was a trained module with sentences and entities. And at the end of that, you have a score. It's exactly like the same as what we have. And then you pick the top n scores, or in this case, maybe top 1 score, and you say that that is the entity that you are referring to. Okay, so instead of, I think that what you are seeing in a lot of the work with, as NLP is improving, we don't just memorize input and outputs, we try to make it read. Okay, the information is supplied, and then we're doing a semantic match. And so that applies to the IR, and it is also in the, in this case, the entity disambiguator. So that was in 2020. You know, things change every other year, right? So by 2022, there's this paper by Amazon. This is refined, and it is an efficient zero-shot capable approach to end-to-end entity linking. It's the same kind of problem, but they added another twist, and that is that they also add type information to the entities. Okay? One of the things you have to remember is that we want to have a description, but sometimes you don't have a description. And the description is not explicit. It's not explicit as a type. So for example, when I asked you, it's like, how tall is Lincoln? And then I say, where is Lincoln, Nebraska? It is pretty clear. How tall is Lincoln is a person. I don't need to know anything about Lincoln. Okay, he turns out to be very famous, but I may not have a description about him. But then, you know, when I say Lincoln, Nebraska, clearly I'm talking about a place. So the type is also very important. So what they did is that it is a representation fine-grained typing. This is the name for their project. So instead of just having candidate entity descriptions, so for example, it talks about D1 is a country that is part of this, the men's cricket team, you know, all these information. But it also has a candidate entity type that just describes what kind it is. You know, the type is pretty good. It's not just a sports team, but it is a cricket team or football team and so forth. Okay. And this is their pipeline. So this is the complete pipeline. So there are two tasks, right? The first one is to find the mention, and the second one is map it to the entity. So in this case here, you have a bidirectional transformer. It takes the sentence, and it first of all marks the mention. B stands for it is the beginning of a entity. O means nothing, and then I means continuation. So what it now is to pull out that we have England and we have FIFA World Cup. Those are the mentions. So that's the first stage of this transform. And at that point here is that, yeah, so you pull out the England and the FIFA World Cup. So this is the first stage is mention detection, just to say it's the begin, inside, and outside. Oh, that's what it means. I is inside, O is outside, tagging. So now you pull out the mentions. And the second one is that you figure out the mention representation. It's using mean pooling. Then the next thing is that it uses the description score. And what they have is a multiple simultaneous bi-encoded representations. Okay, so they are separately encoded, and you're comparing the similarity score. And on top of that, it also looks at the entity typing. It's another score. And this is using L2 distance between the type vectors. And you sum them all up, you combine them. And in this case, it also adds one more thing, which is the entity prior. The entity prior is, what it does is that sometimes you may not have information about something that you mention, but what it is using is it's a global entity prior. It uses a corpus and a popularity metric basically to pull out what everybody knows, okay, what is popular. So if I mention Lincoln, if I just use the word Lincoln, what the chances are I'm talking about Abraham Lincoln. Okay, if I don't want to refer to Abraham Lincoln, I would say Lincoln, Nebraska. Okay, so there is a prior. And if you don't use this prior, all bets are off because sometimes you just cannot tell from the context what am I referring to. So that's the third element that they pull in, and so this goes into the combined score. So recap here is that refine has various stages. The mention detection with the B, begin, inside, outside. And then mention representation via the mean pooling, entity typing, entity description, and finally a linear combination of these things. And that is refined. And it is a very, very useful module, which we have used very successfully in our projects. And what is interesting is that this refined is deployed by Amazon Alexa at web scale. What does that mean? So this is the result here. And as you can see here, in terms of time taken compared to previous work, one is, so the went all with byte encoder or cross encoder and so forth, and Refine just beats them all in this test in both time and performance. So at Amazon scale, we're now talking about populating a knowledge base with 1 billion web pages, and they do this multiple times a year. And it requires 2 days of processing, 500 T4 GPUs. And it is a very uniform architecture. It generalizes to 90 million entities at scale. And that is the refined disambiguator. And we used it, and actually for our project, we also tried to improve it by pulling in information and to augment the data. It is not perfect still.